start. Hello everyone, welcome to Bridges to the Future, I think it is. I have Anna Blum. She's an assistant professor and Alan H. Perot Fellow in the Department of Civil and Environmental Engineering at the University of Wisconsin-Madison. Her research focuses on the analysis of steel, cold-formed steel, and stainless steel members and structures, including metal buildings and steel joists, through computational and experimental approaches, structural stability, and structural reliability. Additionally, she investigates the application of mixed reality in structural steel fabrication. In addition to research, Dr. Blum works on virtual and augmented reality applications for innovative structural engineering education. With her is Will Kraus. He's a software engineer and AR technologist for the University of Wisconsin-Madison. With over 6 years of experience, Will focuses on producing and developing immersive augmented reality software for faculty members who seek to benefit from inserting this cutting-edge technology into their field. Among others, his work includes an underwater 3D scan shipwreck museum, I'd like to see that, exhibit for the Wisconsin Historical Society, and a full-scale tornado and metering from the Department of Atmospheric and Oceanic Sciences, and the steel fabrication system for the Department of Civil and Environmental Engineering and American Institute of Steel Construction. So, welcome. Please give our speakers a hand. Apologies.
Whoa. That's odd. Just start over.
Yes. All right. So thank you, everyone. Today, Will and I are going to be talking to you about how we can supplement steel bridge fabrication with immersive augmented reality. So today, we're going to give you a little introduction to the project, a little bit about the background of what we've been working on, very brief basics of mixed reality and the HoloLens for any of you who are not very familiar, and then we're going to talk about the current project progress. Then we're going to do a really cool demo led by Will, which is going to show you the current project features. And then afterwards, we can have a little discussion about some of the future work and where we should go next. So this project is using research and development on mixed reality applications for the structural steel fabrication industry. This is a collaboration between UW-Madison and the American Institute of Steel Construction. Our learning objectives for today are to demonstrate the various potential applications of mixed reality in the structural steel industry and to discuss the benefits of data visualization of 3D designs in mixed reality. So when we have holograms and they're overlaid onto the real world, we're augmenting the real world. That's AR, but ours is a little different because our holograms are going to interact with the real world. So that is mixed reality because we're augmenting on the real world and they are going to interact with each other. And if anyone here is not very familiar, this is different to virtual reality, where in virtual reality, you're entirely immersed in the virtual world. We need this mixed reality for safety reasons. You have to be able to see what's going on in the fabrication shop around you, and so that's why we're using this technology. Now, the most common mixed reality headset is the HoloLens 2 by Microsoft. You can control with your hands gestures, so no remotes, which is really good because you're going to be working with your hands when you are fabricating parts. It's fully self-contained, so the HoloLens can work on its own, and Will explain that. And also, you can connect wirelessly to other users or other devices. So if you have a project team in the office or elsewhere, you can collaborate with them in real time. So first, we had an initial pilot study, which was supported by AISC's research and technology divisions. And this was a nice collaborative project between structural engineers, me, and software engineers, Will's team. And we found that we could get a 1/16 inch accuracy of the hologram overlay onto the steel parts. And that really told us that we could go ahead and continue with this research because that was the minimum accuracy we needed to achieve to make this viable. Our current study, we then included discussions with fabricators in the Wisconsin area on the beneficial features that they would like to have in order to supplement quality control methods. So supplement, we're not replacing what's currently being doing, we're trying to find a way to supplement it. The goals of the study are to reduce costly errors in a structural steel fabrication shop. And the end goal, and down in the future, is to have free software for AISC member fabricators. Essentially, the steel industry wants to help itself out, so by making free software, it can share among AISC fabricators and hopefully benefit the steel industry as a whole. Now, the applications we're studying are both for buildings and bridges. The demo you're going to see here today is a common bridge application, but we are looking at both building and bridge applications. So the HoloLens 2 can overlay relevant information on that part that you're fabricating and assist with the quality control checks. And this can include bolt hole misalignment, incorrect edge distance. It can display dimensions and measurements. In addition, you can measure distances between points of interest. You can select the points and it can give you a measurement. It can show you the correct orientation of the parts to be connected. What's nice is the display of the user can be live streamed, so you can live stream it to someone in the design office. You can see the shop drawings in the HoloLens. You're going to see this in the demo. And you can do voice to add note at a specific part. So there's something you want to note, you can use your voice and add that in. Table layouts, so you can do a quick check of the individual parts. Also a step-by-step guide to help you fabricate it. And what's nice is you can pull apart this finished connection to familiarize yourself with the sequence and how things go together, so you can be familiar before you actually start welding and drilling holes. This is our demo here is a scaled down version of the connection, but all the features will work fine on a scaled up version. And so with this, I'm going to turn it over to Will, who's going to give you a demo of this with all the features that we just mentioned.
Excellent, thanks. Good afternoon, everyone. Once again, like I said in my intro, my name is Will Kraus. I'm a software engineer. I'm not necessarily in this field, but I'm excited to continue learning in it. And I love augmented reality, mixed reality. And so I helped develop this software with Dr. Blum, a couple other projects that we've been working on together, as well as other faculty members from around campus, turning their ideas into something that potentially is a value add. That's the ultimate goal with this technology. So before I jump into it, I just want to give you a little heads up of what the HoloLens 2 is. So essentially it is a full Windows 10 laptop on your head, essentially. There are no wires connecting to anything else. It is all self-contained. Anything that you expect on a laptop, it's in this device. We have headphones, speakers built right into the brims. You've got a forward-facing camera. You have a microphone pretty close to your mouth. You have a screen, which is just the two pieces of glass that your glasses are. Essentially, it's a 3D set of glasses. The projector is right onto the glass. That's your screen. And then you have a battery pack on the back, as well as normal connectivity like USB, Wi-Fi, and Bluetooth. So the way this demo will work is essentially I'll be streaming that forward-facing camera up there while I go through kind of what we have for our fabrication app. Some notes we have, there's going to be a little bit of a delay. It's like a 3-second delay between what's happening up here and then what'll be up there. Also the holograms, which is what we call the digital objects, those will be a little bit duller in a stream. They just are not as bright as if you were wearing it. And then lastly, we do have the alignment of the 1/16th inch that Dr. Blum talked about, and that'll look a little off in the stream because it's only streaming one eye. It's not streaming both, and you need both for that 3D effect to be accurate. All right, so let me pull up the stream we have going. I'll try not to make you all sick. I'm going as slow as possible. All right, so it tightens down kind of like a hard hat. There is a hard hat version made by Trimble, so that's our 10. All right, so this is a steel fabrication application. It is designed to help out fabricators right on the shop floor, right? And working with AISC and fabricators from around the area, we're trying to determine where it makes the most sense to ultimately improve the efficiency of a fabrication floor, but also reduce the costly errors that arise actually out in the field after it's left the shop. So we're trying to catch all those before it leaves the door, and this is kind of where we decided to start, at least for this application. So we're actually starting with the shop drawings. So you'll find that you have the shop drawings along with a bunch of the different pieces that come along that are needed to make everything that's in this fabrication. It's about 6 pages long, and to try to keep the space a little bit clearer, we just decided to add the shop drawing right into the hollow ones. So you'll recognize there's a bunch of QR codes all over, and that does, it helps with alignment. That's how we're able to kind of transition from the digital to the physical world. But also you can then just read things. I feel a little close with this one, but you can bring things up then, and we could then potentially add a QR code right to the shop drawings, and then there they are. So you can get up pretty close to it. It does follow me around currently. Until I just pin this here. All right, and then you can toggle through them as you'd expect. So you've got all 6 pages there, or if you wanted to, you can expand it. You've got all 6 pages all together. Kind of intense, maybe a little overwhelming, but you're able to then kind of have everything out that you might need. You can expand it, make it as large as you need, and potentially find what you're looking for a little quicker without cluttering your workspace. So there's all 6 pages. But again, that's still not necessarily our ultimate goal. Our ultimate goal really is to take the existing files that are done by designers and actually give all the information that's still in those to the fabricator. Right now it's kind of being lost by being just in 2D. So we're going to bring up the 3D model here that I just put up here. So this is ultimately what we'll be building today. And with the HoloLens, you're able to just pick it up, move it around, interact with it. It's weightless. I learned that steel is heavy, heavier than I expected. So that's why all these are 3D printed parts. They travel better. But you're able to interact with things and get a better understanding of what you're fabricating right off the bat. We also added another feature to be able to interact with the different parts. So if you don't necessarily know how this goes together, if you're a novice fabricator, you're then able to pull things apart and see maybe in reverse order how I'm going to fabricate this. This is more of a bolted steel connection, but if there's more welds, you might be able to interact and figure out kind of what needs to go in which order, right? And work with this in a weightless state. So it also creates kind of cool art too. All right, so that's the interaction. I'm going to turn that off. Set it. All right. So all right, and then I'm going to turn that model off for now. So now we know that what we're actually designing. I'm also just going to get rid of that PDF too. Now let's actually fabricate it. So once again, you have all these different pieces, and you have all of the design information still in the file in the HoloLens. So what we could do then is we can actually lay out all the different pieces on our table here to the exact size that these pieces should be. So what that allows us to do is kind of a quick QA, QC of all the different individual pieces. Let's see. So basically start laying them out, make sure that they actually line up, and they should perfectly match, right? This is just a very quick way to make sure that we have all the pieces and in the right size, the right shape. Good, all the pieces, very good. But it's a very quick way to make sure that your pieces are actually fabricated correctly before you start welding it onto your final fabrication. So pretty good, awesome. One looks like a potential problem. So we do have some, it might be hard to see, but we do have some this alignment here, it looks like on the bottom. So these rows look a little further down than they should be. We can revisit that in a little bit. These two line up, they look pretty good. Awesome, okay. All right, looks good. And then that final piece is right up there for the sake of time. So here are all the different pieces. It's all laid out, it's looking good. Everything looks like it was actually manufactured correctly. Now we should investigate this last piece here because it's just a little bit off. So as Dr. Blum mentioned, you can pull up some measurement points, is what we're calling them. Essentially what we're able to do is we can put this then in line with the calibration square that we have there, and we basically can say this is where we're kind of measuring from, and you can put this QR code basically anywhere on any of the pieces, and this is how we're then able to align the two to get that 1/16 of an inch accuracy between the digital and the physical world. Keep bringing up the start menu. All right, so there's the alignment, and so that is pretty telling that there's definitely a nice alignment of those holes down here. We can even dig a little deeper if we want to, and bring up what we call our measurement points. Again, these are all just kind of wherever we see an important space that maybe needs to be interrogated. So we have center of holes, as well as edges. So for example, I'm gonna make, let's see, we'll do these two here to try to get that center. This is another fun part that we're currently trying to fix, is spaces selecting these measurement points. All right, so that's 5/8 of an inch. And so if I turn the overlays off here, and the table. All right, we can do a measurement quick, pull tape, make sure that, you know, we actually do have a correct piece. Definitely not 5/8 of an inch. I'm not sure how well you can see that, but basically, if we need a new piece, it needs to be fabricated. Dr. Blum, could you hook me up with a fixed piece? That would
There you
be
go.
awesome. How did you do that so fast? Incredible. All right, so let's go ahead and go line this up again. It's already looking better, but we certainly can also do a measurement here of 5/8, and we're all set. Okay, so all the pieces, they're all set up. Once again, I'm gonna just clear that measurement, and then we can bring back our table layout. All right, so we have all the pieces, they're all set up, we're all good to go. Good. And let's finally fabricate it. So for this next part, it's a step-by-step tutorial. We have our steps up here. It's all again in 3D. You can include this in some design files. This one has it, so we have the steps. The first one we've already done, we've already anchored that piece to the strong wall. Now this might not be exactly how you fabricate this together, but these are the steps I took. All right, so the first piece, we're gonna look at which pieces need to actually go in this step. So we're using this high-yield beam here, and we're gonna place this and do the fastest weld on Earth. There it is. Whoa. And all right, that's step one. Step two, got the two red pieces. They're flashing over here on the table, making it pretty clear. Obviously, steel is not all wonderfully colored like this, but all the pieces can still be given a color maybe, or you can have a way to label them. This is just ease of demonstration. I'm just going to throw that on this for a little more stability.
Can you show us the steps you look up?
What's that?
Which step?
Step.
Yeah.
Yep. So this is the current step that we're on.
Okay, so that's the first step. Okay.
Yep. Yep. One more place just to be safe. Excellent. All right. Here's how you'll be. Orientation is this way. So go in. Good. Step 4. Moving on to 5. All right. So this one. Got these 3 pieces. Now a novice might not necessarily realize that right now there's only 2 pieces that I see that are flashing. So I put these 2 out. You can grab this and we'll just take a look to see what that other one is. It looks like, yeah, there it is. Excellent. So it's the same place on the other side. Again, a veteran fabricator likely would know this, but if you're new here, then making sure that you're using all of your parts. And you don't get down the road and realize you have to redo a step. All right, got these 4. You can then reference each, the model, expected, orientation, and which piece goes where. Like that. Right, and the last piece, it's going to believe it's on the other side. No, it's there. I'm just going to place QA/QC feature allows you to ultimately take a look at this final fabricated piece and walk around it, take a look, compare it with the final model. So let's bring up the full design again. And with this full design, we kind of have measurement points here that you also then could use as a QA team and do some simple measurements like this over here on the end to validate that this is actually in the correct place. And now it certainly does not look like I placed it very strategically. But for example, you then pull tape, you realize that it's wrong. And with the Hollands too, you actually have eye tracking as well. So everywhere that you look, you can actually have a cursor, and you can also have a measure phone. So you can then look at some location, which I'm going to look over to the right there, and say the words add note. Usually it doesn't work on the first time, but the second time it does. Add note. No, it's not there yet. Oh, yeah, there we go. All right. Add note. There it is. Look at that. So that's where I was looking. And then we add a little note here. We should be able to then do some speech to text. This piece is misaligned, period. All right, simple note. Future enhancements could definitely include a picture. But that's one way to do it, and of course it's going to take a picture. We also then could look at other places. There it is. Add note. Add note. Still a pilot feature, clearly. But again, it's a simple way to potentially walk around the actual finished piece and add simple notes that then can be sent back to the fabricators to be fixed. So I hope, at least through all these little demos here, you're able to kind of recognize a little bit more about what's possible with the existing files. We didn't modify any of that. This is just data visualization in a different format that ultimately can be beneficial to the fabricator.
Can you put the virtual model on the new guy?
Sure, yep. Should be able to. So like right on top of it, sure.
Yeah, could you use that? So it's a visual check versus like
Sure.
a measurement check?
Yes, yep, absolutely.
Okay,
Sure.
and it'll line it up, or can you?
So not this technically, but that's not a hard thing to have. Yep. Just not built into the app right now.
Okay, I think that'd be something to look at, you know.
Yeah, absolutely. Yeah, it's an interesting,
Because kind of like you do with the parts, you know.
right, see it all, yep. Yeah, the difference with this is, so when you wear the device, there is some transparency potentially, and so it's a battle a little bit between seeing the digital model and trying to see the physical. So it's, if that makes sense. So
Yeah.
when you lay it like this, it's hard to see, or at least in my vision right now, the actual physical object behind it. So having that reference is potentially easier. It's also difficult with longer beams, so certainly the steel bridge connections will be way bigger. And it might be easier to actually shrink that down, but get the right measurement still for a certain part of the connection bolt.
So like for the bolts, is there any way to like encapsulate like the foot-pounds or how much torque is needed to on each of the bolts or in the different points?
Potentially, but nothing, at least from this device. It would have to be an external device to do that sort of measurement.
So you still need to reference like the paper
Mhm.
documentation. Okay.
Yes, yeah. But it could be included as information for the QA/QC person. Yep. Absolutely. Cool. Well, that'll send it back over to Dr. Blum for closing remarks. I can also move this over. Should we just think? Oh.
All right, well, thank you, Will, for that.
Almost.
No. Thank you, Will, for that nice demo. And so some future work we want to continue with this project is integration with standard files, for example, Tekla or other standard design software files that fabricators use. We want to have this include weld information on the holograms, which we currently don't have. As you notice, we focus on bolts. And we want to improve the automatic documentation of any issues and errors to potentially save time. This includes capturing images of any areas that have deficiencies. We want to look at using data analysis techniques to optimize viewable dimensions and information. So there's a lot of dimensions on each connection, but not all of it needs to be viewable at any instance. And so consider if you bring in that data file, what should actually be viewable, what should be viewable at each stage, and maybe what should be viewable depending on where your eyes are looking. And we also want to consider collision identification with other building layers or MEP. And we can do that by integrating with other files. We also want to use this as a training tool. So we want to expand the step-by-step guide for assembly. And we want to be able to record disassembly and you taking it apart so that someone who's experienced could disassemble it in reverse order and give it to someone who could use that as a training tool where they would assemble it based on the disassembly video. And of course, if anyone here has suggestions, let us know what would you like to see or what would benefit you, and we're happy to hear your ideas. We're hoping to make a tool that will be beneficial to the industry. And so we want to acknowledge the American Institute of Steel Construction who funded this research, and I definitely want to give a good thank you to the Web and Mobile Solution, WAMS, which is Will's team, for this amazing development they've done. So thank you, everyone.
We have time for a couple questions. There are any. I was curious, what do you currently use as your modeling environment and workflow to get the model into the?
Together, I see models right now.
Okay.
Yep.
Well, how long did it take you to, you look pretty smooth, I've tried the HoloLens in a few years.
Mm-hmm.
How long did it take you to become as smooth of a HoloLens operator?
That's a good question. I think if I had routine use of it, it'd probably be about a week probably before I get comfortable with it. There's definitely some nuance in it, as you saw, like the start menu keeps coming up and little things like that that just can throw you. And we also have done like a teaching aid for Dr. Blum's students, and getting them to understand it at a quick pace to ultimately actually learn from it, it does take quite a bit of time. So yeah, it's at least a week before like continual use before it's fluid, I would think. Yeah.
By the end of the class period that I had the students use our bolted steel connection teaching aid in,
Yeah.
some students were pretty fast at it, selecting the parts.
Some pick it up faster.
Some did very much struggle, so
Yep.
it can be a learning curve for some, but others are going to catch on right away.
Yeah, I remember the pinching thing, it's like.
Yes. And that's gone, thankfully, with this version. The first one was the pinching thing, and that just gets, there's a lot of false positives being recognized by the cameras of what a pinch looks like, especially if you go like this or like you're holding up like this. There's a lot of problems. Yeah. So, but this is fixed in the HoloLens too.
The other issue a lot of students have is poking
Yeah.
through. And
Because essentially you have to push through a button that doesn't exist.
Yeah.
Like, it's kind of hard to comprehend, and you just kind of have to get comfortable where that spot is. So.
My second more common question, but it seems like those are two, like the training and the using of it in the field. I think both of those are pretty hard. So how are you gonna do both? Have you thought about focusing on one? Because it seems like some good software stuff. I just worry that, you spread yourself too thin.
Yeah, I think it's a good comment. I would say that this is kind of like a prototype potpourri, and we will be going to a bunch of fabricators, and it's kind of up to them at this point, because we've put in all of the effort to show what's made possible, essentially, and what's most beneficial to them is ultimately which way we'll go. So
Yeah, I think you can do VR for training, maybe,
sure, absolutely.
and then an AR for,
And a lot of this does,
real-time fabrication.
sorry, yeah, a lot of this does translate to VR too. I mean, it's all in the same software that can be exported to VR if necessary. So, absolutely.
Do we need more time for questions, or?
One more.
I can ask it later, I don't know.
Yeah, maybe we should move on.
Okay, that's
We gotta do a switch, so, thank you.
Oh, you got me. No, I can look in here too.
this one's yours.
Yeah, that's mine.
Okay, so
Oh, you hooked up, so okay, cool.
yeah,
Thanks. Yep.
All right, next up is Nick Sosa. He's an application developer at GPI and graduated from Stony Brook University in 2018. with a Bachelor of Science in Computer Science with minors in electrical engineering and creative writing. Nick's 4 years of experience in the industry have seen him working on projects that involve algorithm-based geoprocessing calculations, automated feature extraction and geolocated asset information, web-based traffic management applications for local governments, and interactive virtual training programs for the federal government. He's always trying to incorporate his passion for learning new and interesting techniques into his work. Most recently, he's been able to combine his experience developing video games with applications in the AE industry. And got it up and running. Cool. Here we go.
Thanks. Thanks.
Welcome, Nick.
We're going to be talking about our virtual bridge inspection training application today. I'm going to start off real quick with a little bit more about me in case you're not tired of hearing about me yet. I've been an application developer at GBI for about 4 years. Graduated from Stony Brook in 2018. It's up in New York for any of those who are unfamiliar. I've been a lifelong nerd, always been into video games, board games, Marvel, Lord of the Rings, you name it. I've also played hockey since I was about 6 years old, so very much an indoor kid. Fun fact, I've been to more countries than I have states. So a little bit of background on the project. It is for NHI and FHWA, National Highway Institute. It is an application that they use in their 2 of their safety classes, so teaching people how to inspect bridges. It's used at the end of those classes to supplement the training that they've received. It's used in scenarios where an on-site bridge is not available or a specific type of bridge isn't available to give them as close to hands-on training as possible. Our sort of role in this, originally the application was from 2011, so the sort of goal was to modernize the application, make it work on as many types of Windows builds as possible. The original was tied to a very specific build of Windows 7. It ran in a web browser that had a specific version, and it meant that NHI had to ship laptops all across the country, which was costing them a lot of money and a lot of time. So the goal was to untie it from those sort of systems. It was made in Unity game engine, which has informed our choice for development on this. And like I said, the goal was really to modernize the application, touching it where we can to make it a bit more seamless to use and user-friendly. So let's see if it auto plays. No? Okay. So just a quick little video summary here that I'm going to talk over a bit. But yeah, the virtual bridge inspection application, I'm just going to call it the VBI because it's a bit of a mouthful. So like we said, the whole point is to make it possible for people to practice their bridge inspections, put to use the training that they've just received, and use it in classes. And earlier this year, we began work on a virtual reality version. Originally, it was just a desktop application, but NHI has decided they want to give it a go as a virtual reality one and see how it gives different benefits to the desktop application. There's 4 different bridges you can pick from, meant to give you as many different possible defects to find as possible. And you see here, it's simulating having to find your safety equipment. Originally, there was like a 3D model that like, it would put on the different equipment for, but they decided to get rid of that. Have any issues with wanting to customize what it looks like. You can see there's many different tools that the inspectors can use as they go. Hammer, tape measure, markers, chain drag, crack cards, things like that. And the whole point is to make them familiar as possible with the tools that they'll be learning about in the class. You can see there, you can pull up additional information about defects. So if you enter a zone where there would be a defect, you get like a little warning in the top right corner there. And if you hit the appropriate button, you get a bit more information about it. So if you need a bit of a refresher on what this type of defect is, or if you need a recommendation on what kinds of tools to use, it'll tell you that. And this is something that we sort of carried into our virtual reality version that we're still working on. But you can see we're using our lovely tape measure there. There's also plenty of ways to interact with it. So there are points where if you hit it with the hammer, it actually affects the model, and you can get some instant feedback on that. And one of everybody's favorite things to do is just take out the hammer and hit stuff with it because it just feels right. One of the other points that NHI was very adamant about was being able to access the documentation. So normally they have either printout versions of previous inspections or the BIRM, which is Bridge Inspection Reference Manual, and they wanted to be able to access that digitally as well so that they didn't have to worry about printing that out for people, and also for ease of use. One of the main things that we wanted to do was make this as user-friendly as possible, and I'm going to talk about some of the things that we did for that. All right. So some of the technology behind it. I'm going to talk about all of these and sort of why we picked them, but we'll start off here with some of the modeling softwares. So on the left there, you have Blender. It's a 3D graphics software. It's used to make models and animations. We didn't have to use this one too much as part of our sort of contract with NHI. We weren't really expected to change the models too much unless it was absolutely necessary. But you see on the right there are sort of usual suspects with some Adobe products, Illustrator and Photoshop. Those were used for creating textures and creating our menus. So we made our menus completely from scratch. The old ones were done in like a web browser, so we had to completely get rid of those and redo everything. It was also used for storyboarding and creating the layouts. Here we get to Visual Studio and Unity. This is more my area. I'm a programmer, so it's the stuff I'm more comfortable with. But Visual Studio, for anyone who's not familiar, it's called an integrated development environment. It's basically where you write a bunch of code and hope that it runs. Unity is the actual game engine, so it's where we actually put in our objects and attach our scripts to them and are able to reference them in our code and have them actually do things. The benefit of Unity is that it allows you to use a bunch of different file formats. So you can pull in models that exist from other applications, be it things like Revit or SketchUp or things like that, if you're familiar. So what is Unity? For anybody who's not really into games, you might not know. It's something that's primarily used by more independent game developers, but it is used by much larger companies as well. And as part of that, it means that there's a large online presence for Unity in the community. There's a lot of forums and just a lot of ability to find where other people have gone wrong before. Some of the more popular projects that have used it are Ori and the Blind Forest, Hearthstone, which is a World of Warcraft card game, if you ever heard of that, and then Cuphead, which just got its own Netflix show, so that's pretty fun. All right. So I'm going to talk a little bit about our sort of design principles. So when we sort of had our initial discussions with NHI, one of the main pieces of feedback was that their trainees would just sort of go around from one floating orb to another, which is how they previously identified where a defect was on the bridge. So the instructors wanted to get rid of that. They wanted it to be so that it was requiring them to actually walk around the bridge, find these different areas where the defect might be, instead of just sort of pointing and clicking and going from spot to spot. They wanted to add in a way to receive some instant feedback, which is what led to our information screens, those little inspection areas. They wanted it to be easier to move around and control. Previously, you had a point and click to move and use sort of the menu to move the camera, so you couldn't just use the mouse to move around. They wanted to update some of the tools. Some of them didn't function, and some of them were just very unrealistic. We also had to create a brand new menu system, like I mentioned. And something that was a more internal principle for us was that we wanted to make it so that the code base could be used on different bridges. The previous project, the way that it was set up, they had multiple copies of the same files, and it makes it very difficult to maintain. So from a design side, our real main constraints were we wanted to stick with NHI's branding, be very consistent with like their color schemes and logos. And then we also wanted to follow something which is called Section 508 compliance. It is essentially used for websites where it makes things as accessible as possible. It handles things like color contrast, text size, alternative text options, things like that. Another point that we wanted to make sure of was that NHI was involved in the process. So we would involve them each step of the way, especially in our menu systems, letting them pick between a few options so that they could tell us things they did like, things they didn't like, and sort of pick between them. And didn't want to give them too many options because then it's just, you get 5 different opinions and they're all different. But we did our best to give them as many different options, yet doable. So we wound up with sort of a combination of those. You can see we got our giant picture in the background for that main menu, and then we have our sort of bridge preview screens, and then the safety screen with that van. They were very fond of the van. So, all right. Now we're going to talk a little bit about the programming. Again, it's more my bread and butter, so apologies if this part's a little longer. I broke it into 3 stages. Being as a project that we were picking up, we had to sort of do some translation and some interpretation, and then finally some creation, which was really the fun part of it. So when this project was originally done, Unity let you write in JavaScript or C#, and nowadays you pretty much have to do C#. That said, the original code had no comments, so a lot of it was me doing my best to figure out what they meant by stuff because the projects didn't run anymore. So I couldn't run it to be like, oh yes, this is what this is supposed to do. I had to do my best to guess. There were 14 existing tools, each of them unique with a little bit of overlap, so we did our best to sort of consolidate that there. We also had to deal with the navigation and any sort of feedback from the environment, so like those inspection areas, or if you saw it before with the hammer when it hit those blocks that fell, that sort of stuff. So just to sort of explain a bit more with the comments thing, you see on the left side is the original JavaScript. It's all sort of in color. It's Visual Studio taking care of that for you. But you don't see many of those spots where there's that like darker green color. And then on the right side, there's a bunch of it. So all those spots are where I've written in what that sort of section of code is supposed to do. That way, either myself in a few months, if I forget what it was, I can get a refresher, or preferably not, somewhere down the line, someone else has to do it, and they can figure out what it meant. So, the interpretation side of it, we had to update to the newest Unity. Like I said, this is from 2011, so it's been about a decade since then. If I recall correctly, originally it was done in Unity 3. They stopped doing numbers. They started just doing years. So I think that was around 2016, 2017. So it's been quite a few versions to get past that. Some of the techniques that they used just weren't usable anymore. They would call things in the Unity engine that didn't exist, or would call things that were completely changed. So we had to try to figure out what the new method of doing that was. They also used some third-party plugins, which is totally normal, but some of them were no longer available or weren't supported in the newer versions of Unity. And a plugin would essentially be something like handling how water works, so that you don't have to write that every time. Somebody's already done that and letting everybody use it for free. And lastly, some of the tools were broken or unrealistic. So we worked with our instructors to figure out how they were supposed to work and how we could fix them. So just to sort of explain a little bit of how painstaking this process was, you see on the left there, towards like the middle of the screen, there's that like caution triangle saying that it can't read the script. So that's from the original project. But on the right side, you can see a snapshot of just one script attached to the hammer. And all those spots where there's a line sort of giving a title and like it's the thing that's connected to, that's all variables that need to be told what they're supposed to be. In this situation, it was all textures or sounds or different measurements that Unity needed to know what those actually were to perform its actual functions. And we knew none of that. So there were around, I want to say 15 or so materials that we had to figure out and the associated sounds with those. Basically, I had to tell the program what grass was, and we didn't know what the original program called grass. So we had to figure that out. So for the creation side of it, this was where we sort of got to make our own brand new stuff. So like I said earlier, we made our brand new menu system. We modernized the controls so you could actually use a keyboard and mouse. We created the inspection system so that going to an area would actually give you information about the defect that you're supposed to be looking for. We created some base classes. So like I mentioned earlier, a lot of the tools had overlap. So we pulled those into a single parent class to make it so that the tools could be more easily created and not have to reuse the same code. And we also updated to the action system for Unity, which made it so that we could customize controls. This was a big thing for Section 508 because it made it so that whatever needs you have, you can change the control system so that it works best for you. So all told for that, it was around 70 scripts, more than 6,000 lines of code, and over 150 objects per bridge. And that's just like what we had to do and create. A lot of the objects already existed from the old project. So a lot of work goes into these. So with a little bit of info on where we've been, I'm going to talk a little bit about the future of visualizations. So the future is interactive. We have seen before plenty of beautiful 3D visualizations, and the thing that's changing is that you can actually now interact with them. Game engines are catching up to what pre-rendered scenes can do. You see on the top right there, Unity, which is the product we used, recently acquired Weta Digital. If you're not familiar with them, they do computer graphics. They've done the ones for Planet of the Apes. They do like all the Marvel movies, a bunch of Star Wars stuff. So they're a pretty big deal. And they've made this acquisition in order to upgrade Unity's ability to render things as good as possible. The other sort of main gaming engine people use is Unreal Engine. Unreal Engine 5 came out earlier this year. I know it says early access, but I just like that picture. It's out and it's pretty great. So always the issue with these sorts of applications is being able to balance the realism and the performance. You see in the top there a pretty realistic looking human. And as these engines have gotten better, it makes it possible for you to actually run this application and have that good of a visual. But you see below that a scene of a city that has over 100,000 objects. And while the graphics are not as good, it's that increased volume that sort of affects that. So as we sort of talk about realism and performance, you see on the top there we have a pretty recent video game, Last of Us 2 from a few years ago. And you can see just the difference that a couple decades have made. As we look at the bottom there, you see a character from Final Fantasy. And really it comes down to being able to add more polygons to a render and allowing the engines to actually be able to render them. When you're doing it ahead of time, pre-processing it, it doesn't really matter. You can take as long as you want. But when it's something that you're interacting with, it has to be almost instantaneous. And as graphics cards get better, it allows us to actually increase the number of polygons and, as a result, the visual fidelity. So why does this matter for the A&E sort of industry? These companies have seen sort of the love that they're getting from these industries. They've begun making it even easier to import your models from programs that you already use. The whole idea being that, hey, you're already using this model for all of the other work you're doing, why not bring it into our engine, let you be able to interact with it, and do whatever you want. So Unreal Engine has something called Datasmith. It allows you to import models from other programs like 3ds Max, SketchUp, Revit, Cinema 4D, and plenty more. They also have Twinmotion, which is a real-time tool similar to Lumion. The difference, though, is that you can go straight from Twinmotion to Unreal. Lumion, for the most part, is the end of the line for you. You can't really export to other things. And sort of in this same idea, being able to create models from other sources. So a lot of people are using drones to get LiDAR footage or other sorts of building blocks for these models. And then you can bring these into these applications and create a actual real world scenario to then interact with. All the bridges that we have in our application were created a long time ago. We don't know if they're based on a real bridge or not, but using systems like this, you can actually use real bridges, real structures, things like that. You see in the top left there is actually a sort of game that Epic, who makes Unreal Engine, created in an attempt to showcase their new engine. It was in collaboration with the new Matrix movie, and the whole point of it was to show how good a lot of the new techniques they were using made rendering happen. One of the main things that you notice is the lighting. A lot of the time, these lighting techniques take up a lot of computational power, but Unreal Engine has been able to sort of pull that stuff into the engine's actual use instead of putting it all on the graphics cards, and that helps them actually create much more dynamic lighting situations. And you can see on the bottom and the sort of bigger picture there, a little bit more about that lighting and the sort of fine detail that you can still get with these without having to put too much taxing on the computer. I think I might have gone a little bit quick there, but we're at our end. Are there any questions?
Have you looked at Beyond CAD?
So we, in the situation like for this particular project, no. We have a lot of colleagues that do that sort of stuff. They make visualizations and things like that. We're hoping to, when this project wraps up, sort of bump our R&D into this. This is the first project that we've done like this. So it's been a great learning experience for us, but also has been great to see what other things we can do either for this project or similar projects in the future.
Yeah, I just want to kind of see what people are thinking, because to me, what it seems like is it's a Twinmotion, but for civil. The guy who was here last time actually developed it.
Oh.
So, also kind of broke in, because I think Twinmotion, it's kind of similar to Unreal, but it's kind of very civil based.
Yeah, I know Unreal has been trying to make those partnerships and as strong as possible to make other applications be able to port directly to it. So I'll have to check that out. Yeah, to emotion, yeah.
Anyone else?
As you're developing the VR game, what is the biggest hurdle that you're currently facing, or the biggest road bumps to do that transition from just a desktop app to a VR app?
Yeah, so when they originally sort of approached us about this, we looked at it from a sort of opportunity to sort of redevelop the code. We made it so that it was a bit more adaptable. One of the things that we noticed was the way that we were doing the interaction relied a lot on being able to get like specific feedback from like a mouse and keyboard. So we had to change the way a lot of the tools worked so that you could actually use them as if you were using them. And sort of translating from point and click to actual motion swing, or even just being able to 3D look at something. So.
What was the feedback on the vectors?
So we have a few on our team. We haven't used it in front of a class yet because it's just not at that point in development yet. But for the most part, once you put on the headset, it's that situation of, oh, I get it now. A lot of them, have been doing this for a long time and are used to the same old when they're learning how to do it. So it's a sort of a brand new thing for them to get feedback and see. And so far, they've been pretty impressed. We hope to keep that going. Yeah.
Cool. Thank you.
Thank you, guys.
What do you need? Oh, it's me.
I have it.
You think that'll work?
I think it will work. Yeah. That should work. In more ways than one, yes.
This is Shivani Shukla. She has a PhD in operations research from the University of Massachusetts in Amherst. She currently works at the University of San Francisco in their business analytics department. She's the director of the undergraduate business analytics program there. And her research is primarily in cybersecurity and transportation. She utilizes game theories and predictive models for decision making. At the USF Business School, she teaches courses related to data visualization and storytelling. Tableau is her go-to application. However, with increasing work in computer vision, she's starting to get interested in other tools as well. So,
Thank you.
welcome to Shivani.
I'm going to start with a little bit of background that happened like in the last 24 hours. I missed my flight all the way from San Francisco and my laptop stopped working. So this is what I have managed to put together in the past 2 hours. My apologies for the job, but I'm going to talk more than show you if that's all right. So this actually germinated from work that we had done for Cruise Automation, the cruise car company that has began operations in San Francisco. They had been operating their cars at midnight, and they had made it available for students at USF to take a ride or two during that time. So it was from 11 p.m. to 5 a.m. That's the only time that those cars ran. So it started from there, and the question was that what happens to the traffic situation when there's more AVs on the road? So an additional mode of transportation has begun, and what happens to the traffic? There were two theories being discussed. One is that there'd be an increase in the number of vehicles. on the road, and then there could be platooning of the vehicles, so IoT based. Interesting fact, the autonomous cars right now are level 4. They're not a level 5 yet, which means they're not entirely automated. They do require human intervention, and even with the cruise cars, there's humans sitting at some level at some control center breaking a tie if that seems to happen. So if the car just manages to stop along the road, there are people out there who kind of make it go, even though there are no drivers in the cars itself. So it's level 4, and the cars aren't talking to each other yet, which means the IoT that we were expecting it to have is still under construction, under progress. It's a good start. It's actually an excellent start, but we're not there yet. So the platooning of the vehicles, if and when it happens and they start communicating with each other, that would be great. But would they also be able to communicate with the cars that are not AVs? That's another question. And there are all these questions floating around, but people seem to be very, very excited with the autonomous vehicles driving along those streets. So our work was about simulating that stage inclusion of AVs in the traffic and what happens to the possible mode shifts. So this came from the survey that we had done. So these students were taking these rides along, I think, a span of 2 months. And we collected all of this information. What would you do? And then most of them said that access to AVs would help them make existing trips, but also induce trips. So they might make trips that they weren't going to make before. And that raised a question that would that increase the traffic? Because that's sort of the theory around Uber and Lyft as well. Although there's not great data on how much traffic has been added since, there's clearly a pattern there, that there's more vehicles on the roads now that there's an alternative. Like, you don't have to take transit. If you don't want to wait for a bus to show up to your nearest bus station, you could just Uber your way through. So that was a concern. And then 38% said that they would replace their personal vehicles and rideshare with AVs, and 27% would replace transit with AVs. So owing to that, we began the process of simulating. So there were 3 scenarios here. One was the base scenario, so without any AVs, within the traffic to validate and calibrate the simulator itself. The second was, I'm sorry, it says 3 once, but it's supposed to be 1, 2, and 3. AV volume add scenarios, so there's now AVs on the street, and over time the scenario explores the inclusion of AVs into the traffic with the additional volume. What happens? And when is the traffic level F reached, which means that standstill, that there's not much movement. AV dynamic volume scenario. So over time, a dynamic scenario might emerge where there might be transitions. So people might move from one mode to another. The algorithm that was used and the process, let me take you through the process. So what we did is went for all the traffic cam data across the city, captured all that information. And the information that we were capturing was through this object detection model, YOLO V5, although there's a V7 now, which is the version 7. YOLO stands for You Only Look Once. It's a neural network that's the fastest and the most accurate in the market right now in detecting objects. Moving objects, actually, more specifically, because there are other models that do the object detection work really well. But moving objects is a bit of a challenge. YOLO outperforms. And it also, I think, looks at 30 frames per second. So that's on I think, a Titan, Pascal Titan X. It looks at 30 frames per second, which is pretty great. So it was a great model to start with. And the idea here, just to explain this, is to get all of that information. What are the type of vehicles running on the roads? Where are the AVs? Are there AVs? And we took a little bit of liberty where even though those AVs had people behind them, had driver in it, and they were just testing it on the roads, we were still capturing that because we wanted to know the sense of, is it stopping? Is it doing something funky? Is it causing traffic problems? Is it causing collisions? And so some of the problems that seem to be occurring a lot is when the car takes a turn and there's maybe, say, a pedestrian trying to cross, the car stops. Even though the pedestrian might be saying you could go, and things like that. So the lack of that social contract that we have when we're driving or when we're walking is of course missing from the whole equation. So it comes to an absolute standstill. Also, if there's too many pedestrians crossing, usually what people do is, find maybe a spot and take a right or go straight. None of which an AV does. They just stop. So after all of the pedestrians cross, it sort of then decides that at the next light it will start moving, which of course also doesn't work out because now there's more people. So it keeps getting honked at quite a lot, especially if the driver decides to not take a decision and allow the car to take the decision. So that information, so taking all of that information and feeding it into a simulator to see what will happen, and then that was just testing of scenarios, the 3 scenarios that I described. So the way it works, just to give you a short explanation, is it sort of divides the photograph or a frame into grids. Then it creates these bounded boxes around it. It creates a class probability map, and then it does the final detections, which means that it starts to piece things together, that it looks like this is part of the same object within the object or within the frame, and then starts to detect those patterns and go from there. It is based on neural networks, and neural networks outperform almost every methodology in this space. Deep learning has made some great strides, although it's a huge black box, and it bothers me because as a math person, I get very, very uncomfortable when you don't tell me what's going on behind the scenes. I love control. I love controls over my models, and there isn't one here. But the pattern detection is impeccable. I think we don't completely understand the model yet. We have learned to implement. It's funny. We've learned to implement something, but we don't completely understand it. So that little black box part of it is funny, but it does outperform, and it is being used. So we're going for it. So as compared to the others, so the RCNN is the regional convolutional neural network, and so on and so forth. As you can see, YOLO seems to be outperforming all of them. So it not just gives me the highest recall over precision in the models, it also gives me a pretty good AP score. And then clearly humans are way above on the right. We do a much better job at detecting objects and understanding items and things. So this is a little bit of a mathematical background. So it does the confidence boxes. So those B's are the bounding boxes, and then you get the C class probabilities. And then these predictions are encoded as an equation, as you can see. How does it get calculated? So every grid box gets some sort of a value, and then based on that, the confidence is calculated. This is important, and it is important for our models, because if it makes a mistake in identifying the object, it's not like anybody is necessarily dying, because this is happening at a very simulated and a very virtual environment. Having said that, if it doesn't detect it fast enough, that's the problem area. So a funny thing that happened in one of those videos is a pedestrian was walking, and then they were facing this way, their body was facing this way, and they were going to cross, and then they decided they don't want to, and they stood there for a few seconds, and then they turned left again and started walking. The car couldn't catch that, so it jerked itself to a stop because it was too soon for it, and it didn't anticipate this. So if it isn't looking at these more subtle patterns, if the models are not looking at those subtle patterns, this becomes a much more difficult problem for an AV as well, let alone for my analysis, which is a little more basic. So the YOLO that we implemented also detects the speed, and it looks at the direction in which it is moving. It also looks at the size of the vehicle, and we tried our very best to get what the vehicle actually is, especially the rideshare vehicles. So a rideshare vehicle like an Uber or a Lyft looks like a car, and of course is a car, but is it a rideshare vehicle or is it a privately owned car? That question was very difficult to address. The only way we could have done it if it had an Uber or a Lyft label on it, or there was something on the dashboard. But then there were, questions related to the clarity of the image or the video. So the video had to be super nice and very, very clear in order for me to catch that. And not always that is the case, especially if it's raining or if there's too many people around it. I think that also somehow made it more difficult to observe. So this is the actual equation in action, and I'm happy to talk about it as a fellow nerd, if you'd like, but I guess we could go at the implementation. So this is the San Francisco's Castro area, and then similar videos were captured after self-driving operations began in certain areas of San Francisco during the nighttime, and as you know, we also captured their activity during the day, because nighttime, the geographic space was also very limited. So it's doing a pretty good job. I don't think the percentages on top of these things are very clear, but it's able to definitely decipher which object it is and the size of it, the dimensions of it. If you've seen this before, if you've seen YOLO being implemented before, then this might be something that you have seen before. But in addition to what you see here, we also got we made a bunch of changes to YOLO, and we got a sense of what kind of vehicle, what is the dimensions, how much space would it take up on the road, what direction is it going in, and the speed. These are intersections, so obviously, as you can see, the speed isn't very high, but if it is really high, then that part was also a little bit of a challenge to solve. Although it's San Francisco, nobody goes very speedily.
So that doesn't look like it's in real time?
No, this isn't in, when you say real time, what do you?
Well, what were the cars moving at? 20 miles an hour, 30 miles an hour? It looks like they're moving like 5.
Yeah, 5 or 10 or something like that. Yeah. So this is actually, it was happening. It was from a live stream of video cams.
Okay.
So I guess as real time as it can get.
Okay.
Yeah.
It's playing back slower then, right?
Yes, it's playing back slower.
Okay, so you're playing the video back slower. Okay, that
Yes.
was my question.
No. Okay, thank you for that. No, it's playing slower than it actually was. Yeah. Okay. All right. So as I talked about this, we gathered a bunch of information. So we had some severe shortcomings, and I think I also talked a little bit about that. But video quality, the image quality needs to be quite high for this thing to work well. Fortunately, we did get some decent quality images, but I think that would be the next step, to work on a YOLO that can work, or that can figure out objects at least in a very low video quality. Although it could discern objects, it just couldn't identify more things from it. For determining the type of vehicle, the quality of the feed is crucial. It's computationally expensive. It has infrastructural limitations, hence, and there's algorithmic advancement in the space that needs to catch up with the space that it needs. So given that this was an academic study and the resources that I had available to my disposal were limited, this is something that can happen, and it's not a hard problem to solve. While it is computationally expensive and requires a certain level of hardware, that exists. It does exist. It's just a matter of access. So it's my shortcoming and limitation, not the situation in actuality. So this was replicated into a simulation model, which essentially worked. This is speeded up, so this should be good. So it kind of replicated the situation from a few degrees above, and this and other videos that I was hoping to include and I haven't been able to, showed you what happened at each stage of and each scenario. So how did it get, the jams and parts of the day and so on. Okay. So we did model delays and collisions. So AVs usually do get into a slight bit of a collision environment because they get very, very close to another car sometimes when they're taking a right or left. The hardest part of the day for AVs is the school drop-off time. And that's when a bunch of cars in a very small San Francisco road stop and they are unloading children, and then the car starts to go around it because that's what it's instructed to do. But that's not a good idea. It's supposed to just stand behind and wait for it's done. So that was modeled. Some of the other things were, I think it tried to also, so one of the things that it does is when a huge trailer tries to parallel park, it has a tendency to take a right and then come back and then park itself parallelly to the road. So when it took a right, the AV kept going at its pace with an assumption that it's never going to change lanes, which was a little concerning. So all of that was also part of the model, was made sure that it was included in there. And then based on the survey, we knew that 23% would replace either transit or rideshare with AVs, and then roughly 10% would replace private cars with AVs. Again, this is based on a university student level survey, so we do realize that this is also an assumption and a limitation in itself, because student population is in no way representative of the larger population that will be using AVs or driving on the streets. And I think those students might also change their mind within 5 days, maybe. So Euro's results were, we saw that the 72% were cars. Transit buses were roughly 21%, and then the others were 7%. It was difficult to differentiate between rideshare or private vehicles, so there was an assumption there. At times, we had to make assumptions of that kind. So for more than 10 minutes of the accelerated simulation runtime, if the traffic hadn't moved, we saw that AVs with no mode shift caused jammed more than 60% of the simulation runtime. And then if the 10 to 30% shifts happened, it was more than 40% of the simulation runtime, both accounting for new trips as well. So that's about it. Thank you very much. I think to sum it all up, to summarize, we took those video feeds, applied these object detection models, collected a bunch of information as opposed to relying on surveys. One of the things that I'm starting to move away from our surveys because that has too much bias in it, and I'm enjoying the fact that I have tools at disposal that just give me the information. The more latent behavioral information pieces that usually don't come about if I ask specific questions to people. So collecting all of that information, feeding it into a simulation, and then looking at the different scenarios and what seems to happen. I think it's safe to say that they're going to cause more traffic than they're going to resolve the issues, unless there comes a day when we stop using our private cars and move to an autonomous vehicle situation. But this is again from the perspective of people who think that AVs would be only operationalized by companies or private sector. AVs could also be bought. Someday, you and I could go to GM and say, we'd like one of your cars. An autonomous vehicle, I don't want to drive, but I would love to buy a car. Although I don't see why anybody would still be in that mind space where they would buy a car and they don't want to drive it, and it's going to drive on its own. So that's another conversation to be had, but I think that's a more conversation around psychology and policy that I let the experts take care of. So thank you very much for listening. Thank you for coming. I'm happy to answer any questions.
Thank you.
Thank you.
Go ahead.
Were you guys able to use like the default weights and detections for yellow, or did you have to train it yourselves on other images?
At first, we started with the default, but then we had to train.
How long did that training process take from? Because I know, I mean, AI, the longer you train it, the more improved it gets things. Like, where do you find like a good stopping point for training AI?
I don't think I'll reach that stopping point yet, to be very honest with you, because I continue to get the feed and I continue to see where I could improve it. But that's just my researcher brain, I think.
Okay.
Some level, someone will have to call it, and I'm waiting for
Yeah.
to do it. But it's actually reached a pretty good state at this point. The amount of time that it has taken, I think I've been doing that for 3-4 months now. So the amount of feed that it has been fed think it's a pretty decent amount to say things with certain certainty, or at least theorize that this might happen. Some level of confidence.
Yeah, actually, I've got more. I've got loads of stuff to ask you about your YOLO and your custom training on that, but we can do that offline. Did you give any consideration to increase traffic from AVs simply because there isn't an incentive to park them?
Yeah.
So if you have a fully autonomous AV, actually, if you need to go into a store, letting it circle around the block for 10 minutes is not a bad strategy.